All right, for weight is a force, you're going to have to start with this paper, cut the border off, cut out all the pieces at the top. The only thing is keep this bottom section as one sheet. Okay, cut the rest out. All right, so let's start off with one simple, basic, very important fact. Weight is not mass. Okay, weight is not mass. So what is weight? Well, let's talk about a definition. Definition of weight. Weight is the force of an object due to gravity. Gravity. So weight has to do with gravity. Okay, weight, definition of weight is the force of an object due to gravity. Okay, so let's clarify. What is weight? When I say weight, what's the first thing you think? Fat. All right, so you think about your own body weight, okay? And you use one of these bathroom scale things to measure that. Okay? So we're talking about weight. Okay? Usually when we're talking about weight, what are we usually measuring it in? You know your weight in pounds. Pounds. LBS. Pounds. Okay? Well, weight is not the same thing. Alright. Do you remember these scales? Remember the last time we did these scales in the notes? Yes. We talked about mass. Alright? The example we had was the little chihuahua. Talked about the mass of a chihuahua. You put the chihuahua on one side of the scale, and on the other side of the scale, we had two of those mass standards, okay? Two of these things, all right? The standard mass. Each of these 1 kilogram, which tells us that the dog has a mass of 2 kilograms. Okay? So this kind of a scale is what we use to measure mass. This kind of a scale we'd use to measure weight. Okay. So let's go back to the definition for a moment. If weight is the force of an object due to gravity, all right, the units of measure for weight, what are going to be the units of measure for weight? If weight is a force, newtons. Okay, so over here, pounds, well, newtons, all right, pounds, newtons is the metric version of pounds. This is the English system. All right, so back to the top here, we write down weight is not mass. Next to weight, I want you to put a big uppercase N. Newtons is not mass. What's mass measured in? Kilograms. Now you all agree that newtons aren't kilograms, right? They're completely different things. All right. So newtons and kilograms. Weight is not mass. All right, so if weight is not mass, we need to be able to calculate the weight. So, if weight's a force, what is the formula for force? All right, force equals mass times acceleration. I love it. We're going to take that same formula, we're going to alter it ever so slightly. Here it is. Go and glue that in. All right. F stands for force. That little W right there, subscript W, stands for weight. So the force of weight, FW, is equal to, what's M stand for? The mass multiplied by, what's G stand for? Gravity. Okay. What are the units of measure for force? Newtons. What are the units of measure for mass? Kilograms. And what are the units of measure for gravity? All right. Here's your little helpful hint. G equals 9.81 meters per second squared. Acceleration due to gravity on the surface of Earth. Go and glue that over here on the side. Okay? So units of measure for gravity are meters per second squared. All right, let's go back to the formula F equals ma. Force measured in newtons, mass measured in kilograms. What are the units of measure for acceleration? Meters per second squared. So, if we look at this, when we're talking about the force of weight, it's the same formula except we just make that the acceleration is the acceleration due to gravity, 9.81. Okay? It is actually the same formula. It's just this one specifies it's the acceleration due to gravity rather than just any random acceleration. Cool? Cool. All right. Now, what does that all mean? Well, let's do it's a little bit of mental thinking through this through. Okay, so this little piece of paper. Set your journal aside for a second. We're going to do this and we'll glue it in and we're done. The average man is 175 pounds, which is 8.0 kilograms. Okay? To calculate his weight in newtons, we must remember that weight is a force due to gravity. Okay, so this weight, we want to talk about his weight. We're talking about mass. So weight, force of weight, is mass times gravity. All right, his mass. Let's put the man on one side of the scale. Obviously, this is a very huge scale. All right, and we're going to put one of those big, huge iron blocks on this side. Okay. Not 1 ton. He's not that big of a man. All right. But a big, huge block on that side. Okay. We're going to say it's an 80 kilogram block. So what's his mass? 80 kilograms because the scale's balanced out. All right. So what is his mass on Earth?
175 pounds.
What's his mass? 80 kilograms. And I'm doing 3 significant figures in all these numbers. That's the 80.0. All right, what's his weight on Earth in newtons? That's going to require a calculator. So, force of weight equals mass times acceleration. Mass in kilograms is what? 80. Multiplied by gravity, which is? Gives it to you right here. 9.81 for significant figures. We'll just add that 1 in there. And the calculator says? 780 rounded up to 5. 785 newtons. So imagine you ask some guy like, oh, how much do you weigh? 785. You're like, holy cow. 785 newtons, not pounds. Newtons. That's kind of like saying 785 apples. Apples, one apple is about 1 Newton.
Oh, it's 1 pound.
1 Newton.
What if it's like a small apple?
So I said about.
And like a big apple.
All right. Now, this guy's an astronaut. We're going to send him to the moon.
Yeah, boy.
Woohoo! He takes with him his little bathroom scale and his oversized mass scale. And when he gets onto the moon, he steps onto his bathroom scale. Actually, back up. He climbs up onto the oversized mass scale. And what is it going to say? Is his mass still the same?
Oh, it's gonna be lighter. Oh, wait.
Imagine putting himself up on one side, that same block on the other side. Is it still going to balance? Is that block still 80 kilograms? So is his mass what? 80 kilograms on the moon. Now he steps onto the bathroom scale. Is that little dial going to move as far? No. How far is it going to move? Well, you're going to need a calculator to figure that out. All right, so force of weight is mass times gravity, but now gravity is 1.57.
125.6.
So 80 multiplied by 1.57 gives us 125.6 rounded to 126 newtons. Talk about a weight loss program. You went from 785 to 126 in a trip to the moon. But did you lose any mass? No. But you can say, hey, I lost a lot of weight. I mean, heck, imagine that. All right. Now let's send him to Mars. He goes to Mars with his 2 scales, gets on the oversized mass scale, puts the other block on the other side, and he climbs up on one side. And what does it tell us? His mass? His mass on Mars is still 80 kilograms. Okay? Now, he gets onto his bathroom scale on Mars. Is it going to read the same as Earth? The same as the moon? Well, acceleration due to gravity on the surface of Mars is 3.63. 3.63. Multiplied by 80 gives us 290.4. So 290 newtons. So the scale, he's got more mass on Mars, more weight on Mars than on the moon, but on the Earth he still has a lot more weight. Is this making sense, or are you guys completely lost?
Your mass is always going to stay the same.
Ah, very good. Wonderful observation. Your mass always stays the same. Unless, of course, you cut out your liver or something. It's going to pretty much stay the same. All right? Totally kidding. All right. Now, we send him to Jupiter. Jupiter is the largest planet in our solar system and has a very significantly large mass. The acceleration due to gravity on Jupiter is 22.7 meters per second squared. What is his weight in newtons going to be on the surface of Jupiter, if Jupiter had a surface? All right, so 80 multiplied by 22.7, 1,816, round to 20 for significant figures, 1,820 newtons. Holy cow. All right, so if you were ever to go to Jupiter, can you imagine what it would feel like having a weight of 1,820 newtons?
Jesus. Did you gain though? I saw it on Brain Pop.
Your mass is still the same, but your weight is different. What is that like? Okay.
It's because of gravity.
Imagine the last time you were on a roller coaster. And you know how you go all the way to the bottom and then you start going up again suddenly? That moment where you feel like your stomach's going to come out your backside? That is what it feels like standing on Jupiter.
All the time? So
All the time.
You're falling, you're like, what?
No, it's not falling. It's that moment when you've hit the bottom and you're going back up, and your stomach just goes like.
Like in the elevator when it goes like.
Yeah, like in the elevator. Kind of like how that feeling in the elevator when you're going up.
Oh. I thought you were talking about like when your stomach flows.
No, not when your stomach goes. Not when your stomach feels like it's going to come out your mouth. When your stomach feels like it's going to come out the backside.
Oh.
That is what it feels like on Jupiter.
That's scary.
Well, just like you and if you were to send out,
Yeah, you could survive. That won't physically crush you, but it would be exhausting and eventually probably kill you. But it would be hard to breathe. Your organs wouldn't. You'd have to lay down because otherwise you'd actually pass out because the blood would go like out of your head. So you'd have to lay down so you don't pass out, and eventually you'd probably have brain damage. So yeah, not very pleasant. Not to worry. It's not likely anybody will ever go to the surface of Jupiter.
Maybe one day.
Not likely.
Like maybe 2 centuries. Yeah, maybe 2 centuries.
There's much better places for us to go.
5 centuries.
Not that we couldn't. There's just no point.
Large spaces.
All right. Weight is a force. This paper, guys. Oops page. Notice I'm gluing it on the oops page. Not turning the page. Just right there. Glue it on to the oops page. Okay, so do we understand now that weight and mass are not the same thing?
Yes.
Weight is a force because of gravity. You change the gravity, you change the weight. The mass doesn't change. You have to actually lose atoms to change the mass. The weight depends on the gravity. Okay?
Mass is like your body.
Cool? All right.